Hi guys. This is a clip taken from a recent after show over at Jose's channel, which I wanted to share with everyone. Not everybody likes to watch panel shows, and probably even less will see after show material, so it can be easy for good information like this to get lost. What you'll hear is a presentation by Larry Scott, a veteran geodetic surveyor, outlining one of several ways he has measured the curvature of the Earth. As you know, it's common amongst flat earth hypocrites to ask for measurements of curvature, and recently Larry teamed up with Jesse Koslowski and the main surveyor to perform one such measurement using angles to the sun. But in this clip you'll hear about another set of measurements made using the same location data, which provides a complementary result. I don't want to waste any more time here, so I'll just play the clip and let Larry explain exactly what he did.
Can you see it now?
Yes.
Yep. Earth radius.
All right, so they're talking about 3 points in a row and which one's going to be higher. Well, I just put this together the other day for the which I thought was pretty germane to what you're all saying just now. And you may have seen this before. This is the main surveyor up in Maine. Jesse Klosowski went to Taganak, New York. I went to Hagerstown, Maryland. And these 3 points are a section of Great Circle. And I had messed around with angles to the sun, and of course, people like Lemon and Chris Berry, whatever, they say angles don't mean anything. So let's ignore the angles. So let's just measure the distances. Now, measuring distances needs a little, prove that you can measure a distance, I guess. So this is a classic, typical total station, my very cherished massive array of retro mirrors, much like it's on the moon. And I measure that can measure distance, just a pure laser ranger distance. We all like lasers, don't we? And here's an older model, does the same thing, just measures distances. Nice, very old retro mirror. And then I have this. I have 2 GPS antennae and 2 GPS receivers. Now, when I talk GPS measurement, I am not talking about what you get on your phone, what you get with your handheld Garmin, what you get with your handheld Garmin. I'm talking about recording the full radio signal from 10, 12 satellites all at the same time at 2 different locations. So when you measure, when you record the signal independently at one receiver and independently at a second receiver, the 2 receivers are not interacting. They're just recording data, and those 2 data files are brought together in software. And the total station just uses a laser ranger, 872.358, just about a half a mile. Easy peasy, everybody does it, ubiquitous. If I take the 2 data files from the 2 GPS receivers and just extract the distance between the antennae, I get to the millimeter the same answer. So if somebody says, where's your evidence? GPS, you can extract just a pure, simple distance between antennae. Now, this is a total station. Total stations sometimes have built-in electronics and corrections. All right, but if you know anything about them, you look at that little triangle icon, you see this is just the unadulterated slope distance mark to mark, much like this, which also happens to be identical. Now here's my older instrument, which has no such curvature capacity built in. You can see on here a beautiful 1977 manufacturer's label, and it gets the same millimeter. All right. Now, when dealing with A to B measurement by GPS, line of sight doesn't mean anything. The receivers record data independently without any interaction between the receivers. They're strictly, purely independent. So I measure a distance from A to B, and I measure a distance from A to C, C to B, and B to A. Oops. Now, if you look at this, these three distances, this is Hagerstown, Titanic, New York, and Lakefield. Those 3 points are in a straight line. But you notice the distances overlap. The distance from Alpha to Charlie, Charlie to Bravo, added together are longer than the simple distance of A to B by 450 meters. 450 out of 838,000 doesn't sound like a lot. Actually, it is. And when you take those three lengths, you end up building a triangle. And so we get Hagerstown, Titanic, and Lakefield. Notice the triangle. Now the triangle have 3 points. 3 points can also define a curve. And that's when we end up with this. Now, if you build that triangle out of those three distances, you notice 3,000, you end up with 3 isosceles triangles. Triangle on the left, which is A, C, in the center of the earth. And the triangle on the right, which is C, B, in the center of the earth. And then the big isosceles triangle of A, B, in the center of the earth. And notice here, by this simple, and this is high school trig, no angles, hardly, just distances. You notice the distance, what happened? The distance to the center of the earth, 39.58 miles. 39.57 and a quarter miles. 39.56 and 3/4 miles. These 3 points in Hagerstown, Titanic, and Whitefield are all low elevation. This is not on a mountaintop. Titanic and Whitefield are only about 100 feet above sea level, and Hagerstown is about 700 feet above sea level. But the reason why those 3 distances are different is because we're on a spheroid. And so the radius that you get from that if you look at doing the full math and you involve zenith angles to the sun, you notice I get on the left 3962.944, which is an effective radius of the ellipsoid for that 260-mile length. And if you calculate it, you get 3963.08. In other words, not even a tenth of a mile different, or just over a tenth of a mile different. I mean, it's almost exact. And if you look at the right-hand side, you see a little more error, but still only in the neighborhood of a half a mile off of 3964 mile radius. But the point that I wanted to bring up with this, is that this triangle, and of course we have the chord across here, that's 8.5 miles. And if you, quick like a bunny, can figure out 8 inches per mile squared, and the distance from the middle to an end is 260.612 miles. You will see that that is also 8.5 miles at 8.5 inches per mile squared, because 8.5 inches per mile squared is accurate for like 200, 300 miles. It's not a lot different. But I wanted to show how just 3 simple distances measured to a part in a million, half a part in a million accuracy build this very shallow triangle. This triangle is not scale because it's really, really, really skinny. But that's the demonstration of how severe, if I can get back to the beginning, how severe the curve is across these 3 points These 3 points are in a line, but in a line is in plan view because these are 3-dimensional points in space. So these points, I describe them as coplanar because 3 points define a plane, 3 points define a triangle, and 3 points define a circle. So if I just use distances, I cannot get flat. And I'm just using distances. You didn't see hardly a single coordinate on here, just distances. And I can get a distance if there's a mountain in the way. I can get a distance if there's big section of the earth in the way. And these 3 distances clearly overlap because 450 meters, even over 838 kilometers, is grotesque error in my world. Even if that's only a few thousand, a couple of teeny hundredths of a percent, 400-meter error in 520 miles would also, if that were error, then in my 872 meters, that would still be a half a meter of error. So this is coincidentally 872 meters, and the distance from Maine to Hagerstown is 838 kilometers. So it's almost 1,000 to 1 ratio. So if I had a 400-meter error in the long distance, I'd still have a half a meter error here. Now, I'd like to say, I showed you mine, you show me yours. In flat Earth, of course, do not measure anything. And people like Travis said, oh, that takes money, that takes equipment, that takes time, that takes people. Well, yeah, you're looking right there what used to be $30,000 worth of equipment.
Yeah, all I can say, Romer, is welcome to reality, flat earthers. Everything costs money, you know what I mean?
So, and even that, these reflectors, that cost about $1,000 a piece. So that's a $3,000 mirror. That could easily cost $6,000 or $8,000 when it was new. And like I said, the GPS receivers, it used to be a bargain price if you get 3 of those for $100 grand in 1995. Now, these things are available. These things are a little bit obsolete from an operational standpoint, but a newer piece of GPS equipment will not measure better. It can't, because we're dealing with digital signal. It still gets the same fraction of a part in a million. And that's over 1 mile or over 100 miles or over 500 miles. It doesn't have a scalar issue because we're dealing with we're dealing with signals coming from the satellites, which are thousands of miles away, and a separation of a few hundred miles is insignificant in the grand scheme of things. So when I talk about measuring a distance with GPS, I'm going from antenna to antenna. When I'm comparing that to an EDM measurement or a total station measurement, I'm going from instrument to reflector. Straight line, simple chord distance. And if you take those 3 distances from Maine to New York to Hagerstown, and then close that out, you end up with a triangle. You cannot end up with a straight line without invoking hundreds and hundreds of parts per million error. So since I didn't measure an angle, we don't have to deal with lemons. Oh, theodolites aren't any good at distance. We don't have to deal with Gleam and Gary about, oh, the angular distance. There's no perspective here, no angular distance here, no eyeballs, no angles, just a simple distance, which I did demonstrate over a relatively short distance equals laser ranging. And that builds a triangle. That triangle has a sagitta of 8.5 miles. 8.5 miles is very, very, very close to 8.5 inches per square of the miles. So I just thought I'd bring that to the fore. I did get I have seen a couple of times where I'm getting some reference, like on Nathan Oakley and a couple others that, those guys, Kozlowski and Scott, the guy in Maine, all they want to do is show you measurements and diagrams. Travis, don't show me diagrams. Well, I don't know what else to do. I have numeric data. Here's my sketch of that numeric data. And of course, I did measure angles because that's what I do, because the angle on the right is slightly smaller than the angle on the left. Once again, not spherical, ellipsoidal. And the ellipsoid is observable with ubiquitous land survey equipment, not university white paper abstracts. Get an instrument.
Larry, that's a beautiful presentation. I really congratulate you for that. But if there is another, let me ask you a question real quick, brother.
Let me finish. Give me two more sentences.
Earth, and then you're up first, yeah?
2 more sentences. I had done this a couple weeks back, and I only had 2 points. Well, of course, that lit a fire under Jesse. He said, let's get 3. And he hopped in his vehicle, and he drove for 3+ hours, navigated in to getting halfway between, and we set a point, and we made some measurements. And then we realized, okay, he's very close to the middle. He's very close to the middle, but he needs to go about another 60 meters. And we went back on a subsequent day, and again, yielding to the argument that when Eratosthenes did it, Eratosthenes only had two data points, the well and his shadow of the obelisk. And it said, yeah, but 3 points, yeah, that'd be serious. So we put 3 points in a row. We got within to the exact 1,000th of a mile in between, and we got 2 unique angles, and the zeniths represent plumb bobs, and the plumb bobs are not hanging parallel, and they converge at the center of the earth. And in Eratosthenes, he had 7.5 degrees. Notice in this measurement here, we end up with 7.5 degrees because we measured across 520 miles across the surface. And you notice it's just slightly shorter as a chord. And GPS, you may extract the unadulterated distance between antennae, and that is a chord. And I got 2 short chords, and I got a long chord, and the only way to put those together, you end up with a triangle that's got an 8.5 mile sagitta. I'll now take questions.
Okay guys, I hope you enjoyed listening to Larry explain how the Earth's shape can be determined using pure distance measurements. And as always, thanks for watching, and I will see you in the next one.